Hello everybody, my name is Manouchehr Takrimi from ISMRM at Bilkent University, and I'm going to present a programmable set of Z-gradient array and active shield array for magnetic resonance imaging. The motivation is the conventional Z-gradient subsystem consisting of the main coil and the shield coil has limited functionality. The performance parameters of the Z-gradient subsystem cannot be changed, and the high-power amplifier is needed to drive the gradient assembly due to large values of inductance and resistance. Earlier, a Z-gradient array was proposed as the replacement for the Z-gradient coil. It was shown that it's possible to split the main coil into multiple independent windings, where each winding is fed exclusively by a programmable moderate power amplifier, and the resultant magnetic field profile within the imaging volume can be changed dynamically. So as an improved solution, here we propose an active Z-shield array. To have a complete gradient assembly, it's crucial to consider the induced eddy currents. The previous novel solution can be improved by introducing an active Z-shield array. The same strategy of using multiple independent coils with dedicated amplifiers can also be deployed here. And as the hypothesis, by the aid of the active Z-shield array, the proposed set is highly customizable. It can adjust size, position, strength, and linearity of the field within the imaging volume on the fly without causing significant eddy currents. The active Z-shield array can adjust the trade-off between the gradient strength and induced eddy current, and it can be used to boost the gradient strength significantly when the shielding is not necessary. The proposed array set consists of multiple individual array elements for both of the main array and its dedicated Z-shield array. Each array element has its exclusive programmable power amplifier. Using analytic expressions, we can calculate BZ field produced by each element, and we perform constraint optimizations to calculate the best set of feeding waveforms. All the optimizations are based on the target field method, and some extra degrees of freedom can be obtained by varying the relative positions of the array elements or by varying the wire's position in each array element. So, solution parameters, 10 different simulations are presented here to show the flexibility of changing the magnetic field on the fly. In all simulations, each of the main and the shield array consists of 16 bundles of copper coils, each with 6 uniformly spaced wires. A 10 mm cylindrical aluminum shell is added to the simulation to mimic the warm cryostats existence and its eddy effects. All array elements are fed by a trapezoidal current waveform of 100 microsecond rise, plateau, and fall time with appropriate amplitudes limited to plus minus 100 amp. The effectiveness of the Z-shield array is assessed by the residual eddy current defined by the ratio of the B2 to B1, as you can see in the picture. And in the following pictures, the contour maps of the BZ field at the end of the plateau time are shown for the entire Z-gradient set. So in all of these simulations, the linearity error is less than 10% and the residual error is less than 0.025%. As you can see here, this is the cross-section of our coil. This is the main coil, this is the shield coil, and this is the cryostat. Here we can shift the FOV along the Z-axis, as you can see here. With these are the parameters. Also, we can have a trade-off between the maximum field strength and also the DSP size, as you can see here. And also, we can reduce the shield effectiveness and increase the gradient strength to very high values, as you can see here, and in different DSP sizes. Also, we can define double fold regions, and also we can shift the region along the Z-axis. So all parameters are shown in the picture. So as a conclusion of discussion, the benefit of a matched set of Z-gradient array and its dedicated active shield array is sixfold. It's possible to generate a linear or an arbitrary nonlinear magnetic field profile. For a linear profile, it's possible to change the size, shape, and position of the imaging volume and adjust the linearity error. Due to its dynamic feeding mechanism, both the gradient strength and the slew rate are highly customizable. It speeds up the imaging acquisition time since the inductance of the array element is much less than the conventional coil because the coils are smaller. If shielding is less critical, the shield array can be used to increase the gradient strength temporarily. And if shielding is not concerned, the shield array can be fed in reverse mode to achieve very high gradient strengths or slew rates in a short time. Thank you very much.